Hi, welcome back to my statistics class. So today we're going to talk about sampling distribution. So in many fields of study, we cannot this data can use to calculate and estimate, which we use to understand our world. Usually we only connect random sample and then we use to estimate something. Say the mean of a larger population. But what if we connect another random sample? Wouldn't the mean be different than our estimate of population mean? So how could we know that one sample can represent the entire population? So the concept of sampling distribution helps us to understand what we can use one sample to make a statement about the mean of the entire population. A sample distribution is an important concept. It's the probability distribution of a statistic based on a random sample. It describes what if of all possible estimates we could have ended up with. So, for example, if we're interested in the parameter, which is the population mean, variable is the credit hour that SPSCC students are taking per quarter, this quarter. And we have a random sample of 25 students from SPSCC, and we surveyed each student and about how many credit hours are they taking this quarter. So this is the simulation that we have. So on the first graph is the entire population of SPSCC students. And now we're trying to survey 25 students from the entire population. We call it, this is our first random sample, and see the stimulation. So some of them are taking 13 credit hours, some of them are taking 16 credit hours, some of them are taking 20 credit hours, some of them are taking just 7 credit hours. So the second graph is each student, how many credit hours are they taking? And then the third graph, which is the blue point, means the mean of our sample, our random sample, which is the mean of these 25 surveyed students. How many credit hours are they taking? So, like I say, we just take one sample, one random sample. What if we did another one? So this is our second random sample. And see what happened. We survey another 25 students and then take their mean, and then we got another data point. And then we do again, we have another mean of a third random sample, which is on our third graph. So look, so we do another 5 random sample. So from here you can see, hey, we totally did 8 random sample, and the mean of this 8 random sample is 10, whereas the population mean is 16. Okay, standard deviation of the population is 5, and the standard deviation is 7.8. Then we do another 5 random sample, and then random sample, another 5 random sample, and maybe we can try to do 10,000 random sample. So we end up with the mean is getting really close to our population mean. And then the standard deviation is significantly smaller, which means it's not spread as much as the parent population, the entire SPSCC student. So we know that in reality, we can't measure or we can't survey every student. But we will now connect a random sample of a 25 student and survey how many credit hours are they taking and calculate the mean of these 25 students. And we call it, that is our sample mean of the estimate of the population. So now I want to do another comparison. What if we take the sample size of 2 and see what happens? So on the first graph, we have the sample size of 25, and for the third graph is the sample size of it's a distribution of mean with the sample size of 25. And then the fourth one is a distribution of mean also, but with a sample size of 2. And see, let's take 10,000. See what happened. Oh, mean, sorry. Let's do it again. This is another stimulation. If you just take 5, you can tell, compare this to. If you have a sample size of 25, you will have a mean of 15.86, which is really close to our population mean. But if you have a sample size of 2, your mean seems a little bit far off than the population mean. So we do another 5, and then you can tell. And let's try 10,000. So from 10,000, you will see, okay, they both have a really close mean, which is there also 16. However, the standard deviation for the parent population, we have standard deviation of 5, whereas if you have a larger sample size, your standard deviation tends to be smaller, which is 1. But if your sample size of 2, your standard deviation is 3.54. Now let's do another 100,000 random sample and see what happens. So all of these three, whether you have sample size of 25 or sample size of 2, you all have a mean of 16. But the standard deviation is different. That says what? The larger sample size, which is 25, and then the less or smaller standard deviation will be. That means the less spread of the graph is going to be. So let's say, do they fit in a normal distribution? So it seems like if you have a larger sample size, it will be easier to fit into a normal distribution. Okay, so what if we don't have a normal distribution? Let's say at beginning we have a skewed distribution, and let's see what happened. If we have a skewed population, a skewed distribution, not a normal distribution, and then we try to connect the data of a random sample. Let's do one is a sample size of 25, the other is sample size of 2. If we did 10,000 random sample and see what happened. So if the data is skewed, then the larger sample size, then we will have the distribution of the mean is closer than to a normal distribution. However, if the sample size is smaller, like 2, then the sampling distribution doesn't follow a normal distribution. That's by our observation. So now let's look at the node that we have. Okay, so what's the relationship between the various windows? So what is parent population? So the parent population, the example that we have is what? The entire data, all of the data, which is, oops. So now let's take a look. Parent population means our all data, which is all of the SPSS student. And then sample data is the random sample from the population. So in our previous example, we're using our n equals to 25, which is the sample size of 25. In the second example, we use n equals to 2. So the distribution of mean is we connecting the sample means, which is our blue dot. We use the symbol X bar to represent the sample mean from our sample distribution for a random sample. So look at the statistic posted on the left of each window and for which one exactly the mean referred to. What do you differ? What's the difference? So we have our parent population, which is the entire data. From the parent population, we try to estimate the mean, which is the average. We use the symbol mu. And then from the distribution mean, the sample distribution mean, we use the symbol mean with a small s bar. That means the average of the sample mean. Okay, so describe the shape of histogram created when I click and take 10,000 at a time, and in what way does the distribution differ significant from the parent distribution at the top of the page? So remember, when I click 10,000 from the third graph, the second graph is the sample that we connect from the parent function. The third one is the mean of each sample, each sample, random sample, the mean of each random sample. So we know that when I click 10,000 times, it follows a normal distribution. And then the population mean equals to the sample mean. But the standard deviation, remember in the parent function, the graph is more spread out. But for the third graph, it's going to be less spread out with a smaller standard deviation. So what if the parent population is skewed? What does the distribution means look like when n equals 2? And what does the distribution mean look like when n equals 25? So when it's skewed, when the parent function is skewed, we will get another non-normal distribution for our random sample, for a sampling distribution. So, and we can calculate the skewed probability. We can do that. But if we have a larger sample size, it's going to become a normal distribution. In another word, if the parent function is skewed, we need a larger sample size. Okay, so now I want to introduce you what is central limit theorem. So the mean of a random sample is a random variable whose sampling distribution can be approximated by a normal model. The larger sample, the better approximation will be. So remember, when we're trying to, at beginning, we only connect one, two, or five random samples. And then mean doesn't form a normal distribution. But when we click 10,000 times, the mean of the random sample become a normal distribution with a smaller standard deviation. And also, if the data is skewed, but if the parent population is a normal distribution, we don't care about it because the sampling distribution is going to become a normal distribution as well. But if the parent distribution is skewed, then we need a larger sample distribution. Remember our last experience, when the parent population is skewed, the larger sample size the better normal distribution is going to be. Then we will have a better approximation. So there are three requirements for the central limit theorems. One, it has to be independence. So the independence assumption, the sample value must be independent of each other. Second, it has to be a randomization condition. The sample needs to be randomly chosen, or it's not safe to assume independent. Third is the sample size condition. The normal model is appropriate if the sample size is large enough. Later, I will talk about under what circumstance we will consider that's large enough. This is very vague and determined by case. In general, the more skewed distribution is, the larger sample size needs to be. If the population, if the parent population is normal, no sample size condition is required. So if the parent population already a normal distribution, we don't need to consider the sample size. But if it's a skew, or not necessarily skew, or maybe uniform, then we need to consider a larger sample size. Okay, in next class, we will discuss more about the sample distribution. This is just more like introduction, and it tells you what's the concept of a sampling distribution. After this, I will paste a link that another YouTube video about what is sampling distribution of means. I hope that will help. Okay, I'll see you in next class.